Hello, everyone. Welcome to the ILTA Physics online lecture. Today, we are going to study the law of conservation of momentum. Just as the name suggests, this law states that the total momentum of objects remains constant, or conserved within a system, no matter what happens inside that system. Since we are currently focusing on collisions, the event happening inside our system is a collision. Specifically, it means the total momentum before the collision and after the collision stays exactly the same. Take a look at the image on the right. Let's imagine two cars driving in the same direction. If the dark brown car in the back is going faster, it will eventually collide with the car in front. In the diagram, before shows the moment leading up to the crash, and after shows what happens right after. After a collision like this, the front car, which took the hit, speeds up, while the back car, which did the hitting, slows down. The changes in velocity for both cars are represented by the green vector arrows in the diagram. Now let's think about the momentum before and after this crash. Since we previously defined momentum as the product of an object's mass and its velocity, let's look at the front car first. Because its speed increased after the collision, its momentum after the crash is greater than its momentum before the crash. Wait, that seems a bit strange. We said momentum is supposed to be conserved, yet the front car's momentum increased. Then, let's look at the car in the back. Since the back car's speed decreased after the collision, its momentum decreased as well. So, the back car's momentum wasn't conserved either. Then what exactly is the law of conservation of momentum explaining? As you might have guessed, if the momentum gained by the front car is exactly equal to the momentum lost by the back car, the total momentum in the system is conserved when we consider both cars together. This is where the important physics concept of a system comes in. Simply put, you can think of a system as a collection of objects we are interested in. In this case, it refers to the boundary that includes both the front and back cars. I've already given you a big picture overview of everything we're learning today. We will first perform a quantitative analysis of momentum before and after a collision using Newton's third law of motion. Then, we'll calculate the change in momentum when multiple objects collide. And finally, we will wrap up by summarizing the law of conservation of momentum. But first, let's do a quick review of what we learned about momentum in the last lesson. In the last lecture, we derived Newton's second law from the perspective of momentum. We organized the formulas by linking the definition of acceleration from a kinematic perspective with the relationship to force from a kinetic perspective. In this equation, we define the product of force in time on the left side as impulse, and the product of mass and velocity on the right side as momentum. So, Newton's second law can be summarized as the external force applied to an object is equal to the change in the object's momentum divided by the time interval. You can also think of this simply as F equals ma. As I just explained, momentum is defined as the product of an object's mass and its velocity. To put it another way, momentum is a concept like the strength of an object's motion or its mass in motion. Practically, you can understand it as a measure of how difficult it is to stop a moving object. We already know from experience that stopping a large, fast-moving object is much harder than stopping a relatively small, slow-moving one. In other words, the large, fast object has more momentum. Finally, the relationship between the impulse applied to an object and the resulting change in momentum is called the impulse-momentum theorem. Please make sure to distinguish this from the earlier point that Newton's second law describes the relationship between force and momentum. The impulse-momentum theorem states that the impulse applied to an object equals the change in its momentum. and that change in momentum is calculated by multiplying the mass by the difference between the final and initial velocities. A real-world application of this theorem that we use every day is the airbag system in cars. When a crash occurs, the airbag increases the collision time, which reduces the impulsive force felt by the person, even though the total impulse remains the same. Alright, today we're going to analyze the motion between objects specifically from this momentum perspective. Now, let's think about colliding objects. To analyze the motion of two objects before and after they hit each other, we can apply Newton's second law, which we know well. As shown in the formula below, force can be calculated as mass times the change in velocity over time. However, to use this law, we need to know the exact time interval of the collision. But generally, the time it takes for a collision to happen is so incredibly short that it's very hard to measure accurately. Therefore, it's difficult to directly apply Newton's second law to analyze motion during a collision. However, if we apply Newton's third law, better known as the law of action and reaction, we can easily figure out the motion before and after the collision. If you recall this figure, Newton's third law states that if a swimmer pushes against a pool wall with their feet, the wall simultaneously pushes back on the swimmer with a force of the same magnitude in the opposite direction. In precise physics notation, this means the force object A exerts on object B, called Fa on B, is equal in magnitude and opposite in direction to the force object B exerts on object A, called F on A. I want you to make sure you clearly understand the force notation used here. Now, let's use this action-reaction law to analyze a collision. Let's imagine two balls moving toward each other, as shown in the diagram on the right. The two balls collide, and due to the impulsive force of that collision, they bounce off and move away in opposite directions. Now, let's analyze the change in momentum for each ball before and after the collision. For collision problems like this, it's always a good idea to first draw a before and after diagram showing the moving objects. In a before and after diagram, you just need to clearly indicate the velocity and direction of each object before and after they hit. Using this diagram, let's analyze the collision as an action-reaction pair based on Newton's third law of motion. Please take a close look at this long equation below and try to follow along. First, let's focus on ball 2 at the moment of impact. The impulse J2 received by ball 2 is the product of the force ball 1 exerts on ball 2, F1 on 2, and the time duration of the collision. According to the impulse momentum theorem, this is equal to the change in ball 2's momentum, delta P2. Please make sure you're following along with this part. Now, let's analyze ball 1 the exact same way. The impulse J1 received by ball 1 is the product of the force ball 2 exerts on ball 1, F2 on 1, and the duration of the collision. Since the direction of this impulsive force is to the left, we will add a negative sign to the formula. Again, based on the impulse momentum theorem, this equals the change in ball 1's momentum, delta P1. But here, according to Newton's third law, the two forces F1 on 2 and F2 on 1 are an action-reaction pair. Take a look at the illustration in the middle right, showing the moment of impact. Since the collision time delta t is the same for both, the two impulses, J1 and J2, end up having the same magnitude but opposite signs. When we put all these equations together, we can see that the changes in momentum for the two balls after the collision have the same magnitude but opposite signs. In conclusion, the total sum of the changes in momentum in the system before and after the collision is 0. Therefore, we can say that the total momentum is conserved. Based on this understanding, I'll explain the law of conservation of momentum in the next section. Now let's generalize and summarize the law of conservation of momentum. Let's look back at the scenario where two balls collide. However, this time, let's assume there are external forces acting on each ball. As you can see in the diagram on the right, this is a more general system where external forces like F external on 1 and F external on 2 are present. These kinds of external forces can change the total momentum of the system. I'm mentioning the concept of a system again. Just think of it as the group of objects we want to focus on and analyze. In this case, the system is the imaginary area that includes both balls. I'll explain the concepts of system and environment in more detail in another lecture. Let's get back to our system of the two balls. First, focusing on ball 1. If there is an external force acting on it, F external on 1, during a short time interval delta t, the change in ball 1's momentum can be calculated using the impulse momentum theorem like this. In the same way, if an external force F external on 2 acts on ball 2 during that same time interval, the change in ball 2's momentum is calculated like this. Therefore, the total change in momentum for our entire system, containing both balls, is equal to the sum of the momentum changes of each ball. If we simplify this equation, it turns out that the change in total system momentum is the product of the net external force acting on the system and the time interval. If the sum of the external forces acting on the system is 0, then the total change in momentum for that system is also 0. This means momentum is conserved. A system where the total external force is 0 is called an isolated system. So, the law of conservation of momentum states that if the net external force is 0, the total momentum of the system is conserved, no matter what kind of motion or interactions happen between the objects inside. In practical problems, the total momentum is the sum of the products of each object's mass and velocity. So you can just set up an equation where the sum of mass times velocity for all objects before the collision equals the sum of mass times velocity for all objects after the collision. This law of conservation of momentum is a crucial principle for analyzing motion in many types of collision problems. That's it for today's lecture. You guys did a great job. I'll see you in the next class.